So in a previous video, I said that we're going to be talking about all different types of equilibrium expressions and equilibrium constants, and that the Kc was the equilibrium constant for concentrations. That's where the C comes from, concentrations in molarities. The Kp is the equilibrium constant for pressures. That's where the P comes from. Pressures in atmospheres, because we're going to be using the universal gas constant, which has a unit of atmospheres in it. So we are able to convert Kp and Kc using this formula. So the formula says Kp equals Kc times RT raised to the exponent of change in N. So let's just break this down. So the Kp, this is the equilibrium constant using pressure. The Kc, this is the equilibrium constant using concentration. R, this is the ideal gas constant, the universal gas constant, which is 0.0821 liter atmospheres per mole Kelvin. T, this is the temperature in Kelvin. And then delta N, this delta, this triangle is the Greek letter delta. It means change in, so it's final minus initial. And N is the number of moles. So I'm going to write change in the number of moles. So if you've never seen that before, triangle is delta, the Greek letter delta. It means change in, which is the same as saying final minus initial. And when we're looking at a chemical reaction, final is products, initial is reactants. So it's always products minus reactants. So it's going to be the number of moles in your products minus the number of moles in your reactants. Okay, so let's look at an example. So let's say the value of the Kc at 227 degrees Celsius is 0.0952 for the following reaction. And the reaction is methane being in equilibrium with carbon monoxide and hydrogen gas. And the question is, what is the Kp at this temperature? Okay, so again, I like to write out what I've been given and know what my plan is. So I'm going to use this formula because I'm being asked what is the Kp. And this is the only way I know how to solve for Kp at this point, is by using this equation. So Kp is what I'm solving for. Kc is 0.0952. Again, no unit because it is a ratio of products to reactants at equilibrium. Okay, so let's see what else I'm going to need. R, I know, is 0.0821 liter atmospheres per mole Kelvin. T, I know that is temperature in Kelvin. Remember the way that we convert Celsius to Kelvin. Remember, this is Celsius and I want it in Kelvin. So it's always degrees Celsius plus 273 equals Kelvin. So if I say 227 plus 273, it's 500. So temperature, I'll just write that out, 227 degrees Celsius plus 273 equals 500 Kelvin. I'm going to put a little decimal place here so we don't lose any significant figures. And then the last thing I need is the change in the number of moles. So essentially what this is it's the number of moles of products minus the number of moles of reactants. Okay, so number of moles of products is 3. 1 mole of carbon monoxide, 2 moles of hydrogen. So it's going to be 3 moles minus 1 mole of methane. 3 minus 1 is 2. So 2 moles is my delta N. So now I'm going to write out this equation with all of my information in it and solve. So let's say Kp equals Kc 0.0952 times R 0.0821 liter atmospheres per mole Kelvin times, put a bigger parentheses here, times temperature 500 Kelvin. All of this squared is going to equal my Kp. So if you think about everything that's happening here, because Kc is a concentration, which is moles per liter, atmospheres is what this ratio is going to be in, Kelvin is here, and then this is the change in the number of moles, so this is why it's always referred to as the pressure in atmospheres. So now when I solve this, I'm just going to take these two terms, I'm going to say 0.0821 times 500, I'm going to square it, I'm going to multiply it by the Kc, 0.0952, and, whoops, I didn't times it. And I did something wrong. 0.0821 times 500 squared times 0.0952. There we go. And it is 160. So again, if we look back at the number of significant figures, how many significant figures should our answer have? It has 3 significant figures here, 3 significant figures here. But remember, this is the value of Kc, which is a ratio. It's an exact number. So really the number of significant figures in this problem comes from the temperature, which has 3 significant figures. So I would say either the Kp equals 160, no unit, you have to put a decimal place there to give it 3 significant figures, or you could say 1.60 times 10 to the second. And that is how you solve for Kp from Kc.